Happy Tuesday, everybody, and welcome to LambdaConf Global Edition. Today with us we have Natan Silnitsky, and he's going to be speaking to us about Greyhound, which is a new pure functional Kafka library that recently went open source, and so he's here to share about that. Thank you, Natan, for joining us, and we're happy to have you today.
Thank you so much, Courtney. I'm really excited to be part of this. And also, today was the announcement that Zio version 1.0 is out. So a great time to celebrate. And I'm really excited for that as well. The first stable version is an immense milestone. So I'm happy for that. So welcome everyone. My name is Natan Silnitsky, and I'm a backend infrastructure developer at Wix.com. And this talk is about Greyhound, the high-level, pure functional Kafka SDK library. And I'm part of the Wix data streams team, where we recently rewrote Greyhound from scratch using Zio. Sorry. Apologize for that. Some reason it skips the. Sorry about that. Just a second. Okay, maybe now. Great. So. Courtney, maybe I'll start from the start. What do you think?
Yeah.
Sorry?
No problem. I can edit it out. It's okay.
Okay, cool. So, like I said, we recently rewrote the library from scratch using Zio. And you will see in this talk a lot of cool features that Greyhound has to offer and how we re-implemented it using the functional programming style and a few lessons that we learned from using Zio along the way. First, I want to give a few Kafka terms for those of you who are less familiar with how Kafka works. So the Kafka is a message broker that allows to have event-driven style of inter-process, inter-service communication, which is resilient and in a highly available manner. And you can see the Kafka producer on its side produces messages to specific topics. And these topics are divided into partitions. And these partitions are basically append-only logs, where each message is appended at the end of the log. And you can keep messages indefinitely in your Kafka partition if you want, although the default setting to keep messages is for 1 week. And if we look at the consumer side, here we have different consumer groups reading sequentially from the partition at their own pace. And unlike with traditional message queues, they don't remove the message from the partition. They just read it and process it. And once they are done with it, they commit the offset of the processed message so that if there's some restart or the partitions are reassigned between the different consumers, the next message to be processed is the first one that was not committed. And this sequential processing property of the Kafka partitions means it's very performant and can get to much higher throughputs than traditional message queues, as a lot of these messages can be put in the Kafka broker memory. And also, it's really easy to scale up the throughput, but all you need to do is to add more partitions to increase the level of produce and consume in parallel. Great, so that was a very quick intro into Kafka. And Greyhound, the library, it wraps both the Kafka producer and Kafka consumer SDK. And the idea originally was to simplify the API that is provided by Kafka SDK that has a lot of boilerplate with a lot of additional features that were requested over the years by Wix developers to help them with their various use cases, and also to abstract, give an abstraction layer on top of Kafka clients so that it's really easy to change your code in one place and not needed to do any changes for all Wix's services, which now comprises more than 1,400 microservices. So it's really easy to get the changes done to all of them at the same time really easily. And we provide a few different APIs in the client. So we have a Scala feature API and a Zio API, but also a Java API for interrupting the Java applications when all of the logic of Greyhound is implemented using Zio. And additionally, we have the Wix interop layer in order to provide the defaults that Wix developers are used to and allow for the behaviors that we prefer to use at Wix. But that's the only private repository part. Everything else is completely open sourced. And the Wix interop layer has two flavors, both a Scala feature flavor and a Zio flavor, as not all services naturally at Wix are written with Zio. Okay, so let's do a rundown of the features that Greyhound has to offer. So the first, like I mentioned, is to reduce the boilerplate of the original Kafka API. So here we see an example of using the original Kafka consumer. And the first thing you need to do is to create the consumer, specifying all kinds of properties, including the broker location and also the deserializer for the key and the value of the message or record. And once you have the consumer, you can start polling messages from it, polling records in a recursive manner in Scala, of course, where you continuously poll the messages. And once you poll a bunch, you can iterate over them and perform some side effects on them. And you access the record value according to the type you provided. And then once you finish processing, you commit the message. Well, Kafka by default does have the ability to automatically commit for you, but then there is the chance that messages will not get fully processed due to some error that happens in your code or some crash or something like that. So if you want to make sure that messages are processed, then you explicitly commit them after you finish handling them. And if you look at the Greyhound Consumer API, we can see that the user specifies the record handler. It has 4 type parameters. The first one is the Zio environment, the dependencies that you require in your handler logic code. In this case, it's just the console. Then we have the error type for possible errors that can fail this handler. In this case, there can be no error, so the error type is nothing. Sorry. And then we have the type of key that is deserialized and type of value. So in this case, we have some message type, and we can access the message value field. And then all you need to do, once you provided the Lambda for this handler, is provide the handler to the consumer builder, and you have a Greyhound consumer. Now notice that you don't need to explicitly commit the message, as Greyhound will commit the messages for you once you finish the handling. And on the Wix interop layer, we also don't need to configure the broker location, as the Wix layer provides the broker location on a configuration file behind the scenes that is also provided in production with the broker location. So that's seamless for the Wix developer. And so that's a quick show of a very simple way to consume messages. A brand new feature for this version of Greyhound is the composable record handler. So we have the record handler that allows us to have functional style composition, where we have the original user provided record handler and the added behavior, additional behavior that can be composed to it by the Greyhound consumer or by the user if they choose to. So here we can see a list of composing functions that are provided by the record handler, including with error handlers. So this function allows to have specific generic behavior for handling errors. And I want to focus on ContraMap and with the serializers. So ContraMap allows to change the input of the function before invoking the function itself. In this case, we want to change the consumer record types to different types of key and value. And this can be utilized with the serializers, and we'll see how. So the ContraMap implementation is quite straightforward. We have the provided lambda here, where we change the key and value types from key K2 and V2 to K and V. So the implementation of the record handler handle function just invokes the lambda and then flat maps over to the original handle that is called. And when we have with the serializer implementation here, we see that it utilizes the ContraMap in order to deserialize from the chunk of byte to the type that was defined by the user in the deserializer. For instance, the string or some message type that we saw before. A chunk is a Z implementation of a safe and lazily evaluated array. And that's the basic format that Kafka uses, an array of bytes. So we have the deserialization here from these chunk of bytes to the types that are defined by the deserializer. And then we can also map the errors in such a way that we either have the original user provided error, custom error, or a serialization error in the deserializer. And here we see an example of a record handler where the value, the type of the value is duration here. So we need to provide the duration deserializer, and then we are able to access the fields of duration in the handler logic. And the type of the composed record handler here is with a chunk of bytes for both key and value, as we saw earlier that the deserializer allows to get from this chunk of bytes to the user requested types. And these types are then able to work with the message polling done by Greyhound Consumer. It polls the messages in a format of chunk of bytes, and then they are deserialized for the user requested types. And all of this done in a very straightforward style of composition. Okay, so now I want to drill down a bit into the architecture of the Greyhound Consumer and a little bit about its code implementation. So the Greyhound Consumer is comprised of an event loop that goes over, polls messages from the Kafka Consumer, and then it provides these messages to a message dispatcher, which in turn will select the appropriate worker to that actually invokes the user provided code on the assigned message. And we'll start off with looking how the event loop was implemented. So here we see the make function of the event loop that is provided with the Kafka Consumer in the constructor injection style. And it's of type R-managed, so it's a ZIO managed resource that provides for both acquiring the resource and releasing the resource in such a way that we guarantee there is no resource leakage. And if we take a look at the acquiring logic here, we have the recursive method that keeps polling messages on a separate fiber. So a fiber is ZIO, you can think of it as a ZIO very lightweight thread that is much more resource efficient than a thread. And we create a ZIO-ref for a Boolean here. So ZIO-ref is a pure functional representation of mutable state. And we have the running Boolean that we provide to the polling loop. And then we'll get to polling messages. And then here we see the release logic. So once we want to shut down this event loop, we will change the Boolean of running to be false and also perform other kinds of resource releasing here that we want to get into too much detail. But the fiber will then be completed and joined, and all other resources are released. Now, when we run stress tests on the Greyhound Consumer in a production environment with a very high throughput of millions of records per minute, we noticed that there is a memory leak of several hundred megabytes. And we ended up understanding that it's related to this recursive function. So in ZIO, recursive functions are stack safe, but not necessarily heap safe if they are not tail recursive. So if we look at the implementation of poll loop, it had a full comprehension, meaning that it wasn't tail recursive as the last expression was not a call to the recursive method itself. We can see if we desugar the full comprehension here, that it's a sequence of flat maps followed by last map expression, which doesn't really do anything. And thus, this is not a recursive, tail recursive method. So one way to solve this is to use the better monadic for Scala compiler plugin in such a way that when it will desugar the full comprehension, it will see that this map doesn't do anything, and then it will transform it into a tail recursion. But what we decided to do is not to implement the recursion ourselves, just have this poll once function and use the ZIO operator do while to actually perform the recursion for us. And we know that the ZIO operators are all tail recursive and heap safe as well as stack safe. So we thought it would be better to use that instead. Sorry. And one last thing I wanted to mention about the event loop is that using the power of the record handling composition I described earlier, we're able to update the offsets that we require to commit right after finishing handling, invoking the handling of the user code using the and then function composition in such a way that updating the offsets and then committing them is both found in the same place in the event loop. So we have the local reasoning and very clear understanding of the mechanism of the offsets being committed. So this can happen both because of the function composition that is done here, but also because we stated that the record handler cannot fail. It has a nothing error type, meaning that all the errors are handled before when this handle is invoked, meaning that it's safe to update the offsets at this point. So you can see the power that ZIO and functional programming gives us to have very straightforward and simple logic that is easy to understand. And this is really unlike what happened in the previous Greyhound version, where the offset object needed to be passed down deep into the nested classes inside, and then decide whether to update or not according to when errors happened or not, and stuff like that. So it's much more simple and straightforward in the new version when we use ZIO and functional style. Cool. So that was a little bit about the event loop. And now let's go back to our list of Greyhound features. And now we want to add to it the parallel consumption. So that's very important if we want to have good performance. If you take a look at the original Kafka Consumer, then we can poll messages, but we can't do this polling in parallel as the Kafka Consumer is not thread safe. So the developer needs to do the multi-threading or parallel work by itself, or they can create additional Kafka consumers in order to increase the level of parallelism, but that's not really such a resource-efficient manner. So with Greyhound Consumer, we of course utilize ZIO fibers. Like I said, it's the very lightweight version of a thread that's very resource efficient, and also ZIO queues in order to implement the parallel work. So we can see how the message dispatcher and worker implement this parallel consumption. So first off, the dispatcher creates a map of workers, potentially a worker for each topic partition that is assigned to this Greyhound Consumer. And then when a new record is submitted, the worker is lazily created for this topic partition of the record. And once the worker is created, we can submit the record for it to continue processing. And if we look at the worker, then it uses a ZIO dropping queue, meaning that this queue has a limited capacity, and any additional items that are offered to it above the capacity will be dropped, discarded. And this allows us to easily implement message throttling in such a way that if the handling takes a little bit more time, we don't bombard the memory of the running host and potentially cause a memory leak. That's not an issue with Kafka because the message will not, any message that is dropped and not processed will not be committed, so it can at a later stage be offered on the next polling action, and once there is room in the queue, and be processed and committed without issue. So now that we have the queue, we can have the processing logic, which is meaning invoking the handling logic. And that, of course, is done on a separate fiber, a separate ZIO fiber with this fork action. And this means a maximal amount of parallelism possible as the amount of partitions that are assigned to the Greyhound Consumer. And on the Wix interrupt layer, we are able to limit the amount of parallelism if needed by using a simple semaphore to limit the level of concurrency. And just for completeness, we submit the record to the queue upon a request from the worker. And when we compare this to the old worker, it has similar properties here, except that it uses a thread as the mechanism to get parallelism. And this JVM thread is much less resource efficient than the ZIO fiber. It uses a lot more memory, and also as have more and more of these threads, as you have more Greyhound consumers in your app and more partitions that are assigned, it means that the context switch between these threads will be much more expensive. So if for the old Greyhound, we kept by default the level of parallelism for one thread for each Greyhound consumer. For the new Greyhound version, we start off by default for a level of parallelism of 8, and it can be higher because with zero fighters, the level of concurrency here can be much higher than threads, and there's much less bottlenecks to have as many Greyhound consumers and partitions that you want on a single instance. So that's a great improvement with this version over the old one. Cool, so Greyhound offers parallel consumption as well. Now let's talk about error handling. So of course there can be errors, and it's very important for Wix developers in specific to make sure that they are retried. And Greyhound offers a few ways that you can retry handling code that has errored. The first one is non-blocking retry. You can see here it's very easy to set it up. You just specify the intervals by which you want to retry and provide them to the Greyhound Consumer builder. And the way it works is that once the Greyhound Consumer or handler fails processing, then there's a built-in retry producer that will produce the message to a retry topic. And then the message will be consumed after the delay that the user requested. And again, if there's another error, it will be produced to the second retry topic. There are as many retry topics as there are intervals that the user sets. And of course, this is non-blocking, meaning that the original topic can continue processing messages. And this means that we have potential out of order processing. And it's also better to avoid having more than one partition, if you can, per retry topic, because we don't want these retry topics to have a bad effect on the Kafka cluster in terms of the amount of partitions that it has, because it can degrade the performance. You need to add more workers, and restarts take longer time. So we don't want the retry topics to have a big impact on the Kafka cluster. Now, as we see with the non-blocking retries, we have out of order execution. But if order is important for us, then Greyhound has the blocking policy where we can retry the same message upon failure again and again until we succeed. And it's really easy to set it up with the finite blocking and the intervals that you want to set. We can also set it with exponentially backing off intervals or infinite blocking if it's a critical action that has to be completed eventually. And what can happen when you use the blocking policy is that a lag can build up between the producer of the messages and the consumer, because the producer keeps producing more messages, but the consumer is stuck on the same message. So for this, we created a dashboard for Wix developers where they can see the message that currently blocked and decide potentially to unblock it if the message is not important. Or they can go ahead and fix the bug that they notice, and once they deploy, hopefully processing will succeed and the lag will go away. Now, we thought about how to implement blocking retry handling using zero operators. So first we tried to use the zero retry operator that can take schedules, and these schedules can also be composed. So here the thought was to compose this with a predicate schedule that will continue only if the blocking state 0ref allows it to, in such a way that if the user decides to unblock the message, then this will be false and there will no longer be any retries. And of course, there's also this delaying schedule that looks at the interval set by the user that's seconds long or minutes or hours long, and it will delay the execution according to that interval the next time to retry the handling. But unfortunately, this means this cannot really work for our requirement, because once the user decides to unblock, we immediately want to stop retrying and move over to the next message. But when we schedule these delays, then the fiber is suspended and we cannot really interrupt it and move over to the next message, because even if there is an interval set for hours of delay, we can only finish that interval and move on next after that. So unblocking won't happen instantaneously. So instead, we decided to go with iterating over the intervals in a for each while, which means that it will iterate as long as the previous iteration wants it to continue. So the iteration here means handling the message and blocking upon failure. But this blocking is done with checking of the blocking state reference between short sleeps until we reach the interval set. And this allows the user to request unblock and to get a really fast response to the unblocking request, because it's 100 milliseconds between polling of the state. And this for each while flavor of for each is not currently found in Zio out of the box. There are a lot of other for each flavors, but you can see the implementation here is really simple, is that we have the iterator from the iterable, and will only continue to the next item if the result from the previous iteration wants it to. And there is option to use a for each while out of the box with ZioStream. So ZioStream will you have the possibility to convert the iterable to a ZioStream and then apply the for each while on the stream. Good, so we saw how we can retry on consumer handler errors, but what about producer side errors? We have rare cases where the Kafka producer broker, is unavailable. And for that, Greyhound offers a resilient producer. So let's look at the use case that describes the need for this resilient producer. So we have the Wix payment service that is working on subscription renewals of Wix users, and it has this job scheduler that invokes it whenever a subscription needs to be renewed. So the first thing that the Wix payment service will do, it will produce the message to the Kafka broker, and then it guarantees that the message will eventually get consumed and processed without any timeout or something like that. And we can utilize the retries we described earlier in order to make sure that the consuming and processing will eventually succeed. But producing can fail on rare occasions where the Kafka cluster is unavailable. So for that, Greyhound has the resilient producer that first saves the messages to a local buffer on the disk. And the default implementation is the H2 file database. And then it reads messages from the local buffer, produces them to Kafka, and will retry in case of failure. So this covers also producer-side errors. And one last feature I want to mention is context propagation. So this is very important for us at Wix, where we have this use case, for instance, of some site visitor wants to sign up for the Wix site, and the site member service gets the HTTP request, and it has a lot of request headers like the user language, the geolocation, and the user type. Is it a site visitor? Is it a Wix site user? So all of this information is found on the request itself. And when the site member service uses Greyhound Producer to produce this to Kafka, it will automatically get all of the request context serialized into the Kafka record headers. And then the context service that manages all the contexts for the week's user uses the Greyhound Consumer and automatically gets all of the request context deserialized from the record handler, and it's available for it to use, maybe persist the information to database. And here we can see the implementation with the Greyhound Consumer. So first we get the context out from the record headers, and then we can easily add the extra request context dependency to the record handler via the Zio environment and the Zio layer. So we just add the additional context Zio layer to the Zio environment that is used by the record handler. So if we look at the example here, we have the record handler able to retrieve the context from Zio environment and then use it for, let's say, uses the context to write the information to a context DB. So the Zio environment type in this case is the user injected dependency of context DB along with the request context that was injected by the Greyhound Consumer itself. And a few more features that Greyhound has is the ability to pause or resume consumption if your application has health checks, where, for instance, you have database connection that suddenly goes offline. You don't want to keep consuming and having more and more of these errors on the database. So you just are able to automatically pause consumption on a health check failure. And also, Greyhound offers a rich set of metrics that are reported, including the currently longest running handler time. So you can easily understand if you have a stuck handler or some bottleneck handlers that go to and that cause increased lags between producing and consuming to make you able to debug this, and all kinds of other metrics that make it easier to debug production and understand what's going on, which is really important in event-driven systems. And we also want to complete migration of features from the old Greyhound to new Greyhound, including implementing a batch consumer and exactly once processing, meaning that we want to be able to process messages exactly once in order not to need to deduplicate logic and stuff like that. And also the in-memory key value store that we have, which is an implementation of zero latency in-memory access to a key value store that is implemented on top of Kafka compacted topics that serve as a kind of storage of key values. And implementing all of these will be much simpler by using Zio with the shorter syntax and much more ergonomic environment. So Greyhound Producer and Consumer are used by almost all microservices at Wix, so more than 1,400 microservices. And there are a lot of various use cases that use Greyhound in versatile manners. We have the classic PubSub, where the service will subscribe to interesting domain object events that it's interested with, some creation event or update event. And also the offline scheduled jobs use case I described earlier, and any action that you want to retry and make sure that it's complete successfully, you use Greyhound for that. And also a lot of database interaction, including change data capture. So you emit Greyhound events when you write to the database, and then this allows to get consumed and maybe create materialized views on other databases like Elasticsearch. And also Greyhound is the bedrock of our cross-DC replication between Kafka clusters. So one instance is replicating the Elasticsearch data through Greyhound between different data centers. So Greyhound is used by many use cases at Wix. It's battle tested and proven and quite reliable. And rewriting it in Zio resulted in much less boilerplate, code that is easy to understand, as it offers a lot more local reasoning and high-level concepts that are easy to follow and understand. All you really need is to have the basic idea of how Zio works, like Zio 101, and then it's really easy to move around and understand how the Greyhound Consumer is implemented, unlike the previous version that was much more cumbersome to understand because it had a lot more boilerplate, a lot more moving parts to do exactly the same thing. And it was also quite fun to implement with Zio with the very ergonomic environment. Sometimes you can't exactly do what you are required with the high-level Zio operators, like the retry with the schedules that I showed. But Zio offers lower-level abstractions too, like promise and clock sleep. So anything that you can do in Scala, Java, with the concurrency primitives Java offers, you can also do in Zio in a very similar fashion. So it has both levels of conceptual work. And Greyhound is open source, like I mentioned. It's currently in version 0.1. So it's not the 1.0 stable version that Zio has reached, because we are still maybe changing APIs as we go along. But you can go ahead and check it out on this link. And thank you very much. And if you want to check out these slides again, you can see them on SlideShare. I uploaded them. And you can follow me on Medium and Twitter to get updates on what data streams team at Wix is up to in terms of event-driven programming, Kafka, and also functional programming and Zio, which we love to update on. And if you want to check out previous recorded sessions I gave on Kafka and other subjects, you can find them on our website at natansil.com. So thank you again. And Courtney, if there are any questions, I'll be more than happy to answer them.
Wonderful. Thank you very much, Nathan. We're really excited about Greyhound and really excited with all the different examples and integrations you've shown. So thank you for letting us hear about Greyhound.